Hydrogen is an element with only one valence electron outside the nucleus. The ionization losing electron. Energy of hydrogen is 1,312 kilojoules per mole, which is so high that H plus, or say proton, is not supposed to exist at an ordinary condition. The proton in aqueous solution is actually hydrated, mostly with a structure of H3O plus called hydronium ion, which is confirmed by experiments. The enthalpy for a proton to be hydrated is about minus 191 kilojoules per mole. Indicates the hydration is favored energetically. The hydrated species of proton also include H5O2 plus and others. The electron affinity, energy for gaining electron, of hydrogen is minus 73 kilojoules per mole, compared with the higher ionization energy of hydrogen. In the binary hydride of S block metals and hydrogen formed directly by heating metal with hydrogen gas, the anion is H minus hydride ion, and the cation is metal ion. The average radius of H minus is about 133 picometer, very similar to that of fluoride ion. There are three isotopes of hydrogen: protium, denoted by H, deuterium by D, and tritium, T. The isotopes of hydrogen exhibit larger differences in physical and chemical properties than isotopes of any other element. Such differences are attributed to the isotope effect. Generally, the bond between two deuterium atoms is stronger than the bond between two protium atoms. Deuterium bond with any element is stronger than protium bond, which induces a difference on reaction rate. Dihydrogen, normally in gas state, the value of the melting point, enthalpy of fusion, boiling point, and enthalpy of vaporization are all very low. Nearly all elements except a few form binary compounds with hydrogen. Hydrogen is not reactive kinetically rather than thermodynamically. The well-known explosive reaction of the hydrogen and oxygen initiated by sparking is a good example. The reaction rate is extremely high after the reaction is initiated, although the reaction contains many elementary steps. Another example for inert hydrogen is ammonia synthesis. The proper catalyst is essential to speed the reaction. No catalyst, no reaction. The right catalyst can break the bonding in hydrogen at low cost. The graph shows how the hydrogen molecule approaches to the surface of catalyst, attach on, and break into two atoms, ready for further reaction. Hydrogen atoms are small enough to occupy the interstitial holes in the metal lattice, and the absorption of hydrogen by metal leads to the formation of metal hydrides, in which hydrogen atoms reside in interstitial cavities. The metallic hydrides could release the hydrogen upon heating. The absorption and desorption of hydrogen is reversible, which can be applied for hydrogen storage. Non-conducting silent hydrides are formed when the group 1 or group 2 metals, not beryllium, are heated with hydrogen, or are white, high-melting ionic bonding solids. The reactivity of the group 1 hydrides increases with an increase in atomic number and the ionic size of the metal. Saline hydrates react immediately with protic solvents such as water, ethanol, even halides, showing that the H- ion is an extremely strong base. See the chemical reactions shown here. Covalent hydrides with discrete molecular structures are formed by the p-block elements in groups 13 to 17, except aluminum and bismuth, for example, methane, ammonia, water, and hydrogen, fluoride, etc. Most molecular hydrides are volatile and have simple structures compiled with the VSEPR model. But for boron, it dimerizes to give diboron, or even it polymerizes. Let's have a look at the bonding in the diboron. See the chemical structure given here. We notice that each bridging H atom is attached to 2 boron atoms, despite having only 1 valence electron. Each boron atom is attached to 4 H atoms, though having only 3 valence electrons. And the bond length of boron and hydrogen are not all the same, suggests 2 types of boron-hydrogen bonding. It's found that 2 electrons occupy a bonding molecular orbital that delocalized over 3 atomic centers. The bonding between the 3 atoms is called 3-center 2-electron bonding, or 3C2E bonding. It's weaker, so that the bridge bond length is larger than the terminal one. This bonding pattern is also seen in some other hydrides.